here to discuss about instruction set. So instruction set are machine codes. It is a complete set of instructions that are understood by CPU. And usually it is in the form of binary. Next, there are different elements of instruction. So the first is the operation code. Operation code, or tinatawag din na opcode, ito yung mga gusto mong ipagawa sa computer mo. So usually ito yung tinatawag na do this. The next is yung source operand, or yung do this. O dun mo sinasabi kung saan ba ilalagay yung data. Then is the result operand reference. Ito yung put the result here. O, dito mo ilalagay yung pinaka-data mo. And yung next instruction reference, syempre, after nung gusto mo ipagawa, meron pa yun na kasunod. So, meron ka pang gustong pagawa. So, yun na yun. So, now let's move on to the different types of instruction. So, first is the data processing. And ito yung mga arithmetic and logical instructions na binibigay mo sa computer. And next is the data storage. So, from the word storage, syempre, dito mo ini-store, dito mo sinesave yung mga data na nagagawa. And the data movement, ito yung nagko-control sa paggalaw ng data mo from input to output. And the program flow control, so, dito ginagawa yung mga mga instructions such as call and return. So, dito naman tayo sa number of addresses. So, meron siyang 4 na klase. So, una, yung 3 addresses. So, sa 3 addresses, yung dalawang address, mag-serve siya as source, yung isa ay destination. So, example is equal to B plus C. So, si B, saka si C, sila yung source mo. Then, pag pinag-add mo sila, papupunta siya sa destination na si A. And next, is the 2 addresses. So, meron kang dalawang address. Yung isa, serve as a source. Yung isa magsaserve siya as source tsaka destination. So, kung dito, meron kang B tsaka C, si B tsaka si C, yung source mo. And then, pag pinag-add mo sila, yung sagot nila, ipapasok mo rin siya kay C. So, meron siya, source mo na siya, destination pa. Then next, yung 1 address. So, yung 1 address, meron kang isang source, and then yung isa mong address ay automatically binibigay na ng CPU. And yun yung usually tinatawag na accumulator. And next is 0 address. Walang source na, wala kang kahit anong source, and lahat ng address mo ay galing lang mismo sa CPU. So, yun. Ito naman tayo sa design decision. So, ito yung mga dapat mo sa alang-alang sa paggawa mo ng design ng instruction set mo. So, una, operation repertoire. So, dito, isipin mo muna kung ilang operations ba yung gagamitin mo. Ano ba yung mga dapat niyang gawin, tsaka kung gaano ba ka-complex yung mga operations. And next is yung data types. Ano-anong data types ba yung gagamitin mo? And sa instruction formats, so kung gaano kahaba ba yung operation code field mo, tsaka kung ilang addresses yung gagamitin mo. It's either 3, 2, 1, or 0. Then next is yung register. So, ito isipin mo ilang register ba yung available na pwede mong gamitin. Tsaka anong operation ba yung pwedeng gawin sa bawat register. And addressing modes na explain pa mamaya. And yung RISC versus CISC. So, RISC yun yung Reduced Instruction Set Computing versus Complex Instruction Set Computing. So, isipin mo, alin ba dun yung gagamitin mo? Either yung reduced or yung complex. So,
hi, I'm Mark Soriano and I'll be discussing about the data types of ARM and x86. Okay? Okay. x86 assembly has no predefined data types like higher level programming languages like Java, C++, C, and anything that is much higher than assembly. Okay? x86 is any general purpose register that can hold any sequence of 2 or 4 bytes. Whether these bytes represents numbers, letters, or other data in the same way. There are no concrete types assigned to block of memory. You can assign to them whatever value you like. Okay, and I will tackle that later in my discussion. And we proceed now to ARM. And also, x86 is also a example of CISC or complex instruction set computer or computing. And then we proceed to the ARM. ARM means a long time ago, ARM means Acorn Risk Machine, and now we call it Advanced Risk Machines. ARM is also an example of RISC. That's why in R it means RISC. Okay, do you get? Okay, if we want to create a variable or a word variable, we use char, and in x86 we use define byte. And now proceed to the DW. DW stands for double word. It corresponds to the int. So if we are using DW, then we were making a variable that is a number. Okay? Int or DW is from 0 to 255. Now, before we proceed to DUP, let's proceed to DQ or correspondent to the double data type in C. And when we say double, we are using decimal point on a variable. Example, in int we can only get the whole number like 1, 2, 3, and so on and so on. And then in DQ, in double, we get a 1.0, 1.25, and any decimal place and any numbers that has a decimal value. Okay, now let's proceed to DUP. DUP is same as an array in C. Example of this is that this is the defined bytes that you can allow, or you are allowed to allocate multiple bytes in DUP. You are allowed to allocate multiple bytes. Example of this is that I have this defined byte, DB, and I'm assigning to have a 5 values of defined bytes. So these 5 values, this 5 will go on to DUP. And now the value example is that DUP, and these are the variables. Sorry. It has a 5 located variables inside the DUP. Okay? Okay, let's now proceed to ARM data types. ARM processor supports data types of 8-byte, 16 half-word, 32 word bits in length. And then, in alignment checking, when the appropriate control bit is set, a data abort signal indicates an alignment fault for attempting unaligned access. Later, I will explain that. And then, all 3 data types can also be used for 2 complements unsigned integers. Then, unaligned access, when this option is enabled, the processor uses 1 or more memory accesses to generate the required transfer of adjacent bytes transparently to the programmer. Okay? Let's now proceed to the examples of data types. these are the ARM data types. First, we have a car, and its size, these are the size, and the car size in bytes is 8, and the alignment in bytes is 1 byte align. Okay? As we all know that car is used for words, for allocating words for variable, and then short, it has a 16 bytes, which is smaller than the int. Short is smaller than the int, and int is smaller than the long. These three are both used for declaring a number declaring a number. Okay? Short has a byte size of 16, int 32, and also 32 is long. And the short has a 2 half-word align, and int and long has a 4-word align. And then we go to the long. Okay? Long is also like as long, but long is much higher or much greater than long, because long has a 64 size in bits and 8 double word align. So, and then we have a float, 32 4-word align. The difference between float and int is that float has a decimal value and int does not have. And float, double are also like, but double is much bigger than float because it has a size of 64 bits and it is 8 double word align. And then long double is also like this, also like double and float, and it has a 64 bits also and 8 double word align. Okay, these are the data types of ARM. Okay, let's now proceed to Intel x86 operation types. There are 4 parts: the data movement, arithmetic, logical, and control transfer. We talk about first is the data movement. First of all is the move, MOV. MOV operand between register or MOV move operand between register or between register and memory. Then the push operand onto stack, and push A. Okay, let's now proceed to all string operations. It also has a move S and load S. It is also like a move and LEA in data movement, but in this we're moving a string operation. In MOVS is we're moving a byte, word, D word or string, and when we said LODS, we're loading a byte, word, D word or string. Then in the protection, we have SGDT, string, or which means string global descriptor table, and LSL, which is load segment limit, loads a user specified register with a segment limit. Okay? Okay, these are the x86 operation types. And now we proceed to ARM operation types. Okay, let's now proceed to ARM data operation. There are 3: operation on basic data types, operation on integral type, operation on floating point types. And we go first on operation on basic data types. The ARM compiler performs the usual arithmetic conversions set out in the relevant section of the ISO C99 and ISO C++ standards. And then we go to operations on integral type. All signed integer arithmetic uses a 2 complements representation. Bitwise operations on signed integral types follow the rules that arise naturally from 2's complement representation, no sign extension takes place. Right shifts on assigned quantities are arithmetics for values of type int. Shifts outside the range 0 to 127 are undefined. Left shifts or more than 21 or 31 give a result of 0. Right shifts of more than 31 give a result of 0 from a shift of an unsigned value or positive signed value. They yield -1 from a shift of negative signed value. For values type long, shifts outside the range 0 to 63 are undefined. The remainder on integer division has the same sign as the numerator as mandated by the ISO C99 standard. If a value of integral type is truncated to a shorter signed integral type, the result is obtained by discarding an appropriate number of most significant bits. If the original number is too large, positive or negative for the new type, there is no guarantee that the sign of the result is going to be the same as the original. Conversion between integral types does not raise an exception. Integer overflow does not raise an exception. Integer division by 0 returns 0 by default. Okay, we go on now, operation on floating point types. The following statement applies to operation on floating point types. The following statements apply to operation on floating point types. First is, rounding is to the nearest representable value by default. And then, floating point exception are disabled by default. And these are the ARM data operation.
These are the types of operations: data transfer, arithmetic operations, logical operations, conversion operations, input and output operations, system control operations, and transfer of control operations. The first operation is data transfer. For this, we need the source, the destination, and the amount of data. For example, MOV, which stands for move, is an operand. 7, we are going to move the value 7 into the array 0 of EBX. Like in other programming languages, arithmetic operators also exist in assembly language. There is addition, subtraction, multiplication, and division. For example, A equals B plus C. B equals A minus C. C equals A times B. Go. And D equals A divided by B. The logical operators. This is the table for the AND, OR, and NOT operators. This is an example of the AND operator. A and B. If there exists a 0 in at least one of the values, then the result will always be false. Unless both of it are true. True plus true is true. See this? Okay na, next na.
True plus true, pre.
And here is an example of the OR operator. A or B, if there at least exists a value that is true, then both of it is true. And for the NOT operator, it provides the opposite value of what you have produced in another statement. Conversion. Since we already discussed about the number system, I'm not going to explain this further anymore, as we already know how to convert these values to these values.
Addressing modes. Addressing modes are an aspect of the instruction set architecture in most central processing unit designs.
Meron tayong tatlong basic na addressing modes. Ito ay register addressing, immediate addressing, memory addressing, and post.
Register addressing. In this addressing mode, a register contains the operand depending upon the instruction. The register may be the first operand, the second operand, or both.
For example, ito ang opcode natin, yung move, yung code na move. Tapos ang operands natin, itong dalawang to. At ang register natin, ito. So, ang register niya ay nasa first operand. Ang first operand ay ito at ang register address natin ay ito. Sa pangalawa naman, ang register address natin nasa pangalawa. Dito, pwede siya dito. At sa pangatlong instruction set naman, ang register natin ay nasa dalawang operand. So, pwede to. Ang susunod nating addressing ay immediate addressing. An immediate operand has a constant value or an expression. When an instruction with two operands uses immediate addressing, the first operand may be a register or memory location, and the second operand is an immediate constant. The first operand defines the length of the data. For example, ito, byte value DB 150. Ang DB natin, ang keyword DB natin ay nagde-define ng char. At ang kasunod na linya ay ang kasunod na memory addressing natin ay direct memory addressing. Ang direct memory addressing, when operands are specified in memory addressing mode, direct access to main memory, usually to the data segment, is required. This way of addressing results in slower processing of data. To locate the exact location of that data in memory, we need the segment start address, which is typically found in the DS register in an offset value. This offset value is also called effective address. So, skip na tayo dun. So, ang sample ko dito ay add byte underscore value DL. Yung value niya, yung register value nito, yung register value, i-add mo dito sa memory location. I-add mo. So, ma-add siya dito. So, parang madadagdagan to, yung value na ito. Kasi itong move dx word value, ang ano naman dito, ang ito naman ay madadagdag dito sa ang susunod nating example ay move bx and move bx with word value. Ito ang memory location natin. Ang memory location natin ay may mamumove dito sa register address natin. Susunod nating addressing ay tinatawag na indirect memory addressing. Ang indirect memory addressing, this addressing mode utilizes the computer's ability of segment offset addressing, generally the base register EBX, EBP, or BX or BP, and the index register DISI, coded within square brackets for memory references, are used for this purpose. Indirect addressing is generally used for variables containing several elements like arrays. Starting address of the array is stored in, say, the EBX register. The following code snippet shows how to access different elements of the variable. Ang ibig sabihin nun ay parang sa array natin siya ginagamit. For example, mag-declare tayo ng array. My table 10 is, which is the memory location, 10, allocates 10 words, and DW define words, which is data type for defining a card, and 0. Ang ano niyan, ina-allocate niya yung 10 words, which is each initialized to 0. So yung size nito na 10, bali may table, tas 10. Yung 0, 1, 2, 3 hanggang 10, ang value nila ay 0. Susunod naman na linya ay ang move EBX with my table. Ang ano na ito ay, ang keyword na EBX kasi ito ay ginagamit sa indexing, which is array. Ito ginagamit. So ito na siya. May value, nakastore na siya sa register na EBX. Ang EBX natin ay ginagamit to sa array. So let's proceed to the next slide. Move EBX 110. Wala pang value yung natin, may table. So parang siguro default na siya, 0 siya. Move EBX 110. Ang EBX natin, ang may table pala natin, kasi may table to eh. Index 0 ay equal to 110. So, ganyan siya kung mag-declare ka. So, proceed to the next line. Add EBX 2. Parang ano lang yun sa Java. Parang ganito. Ipa-plus lang niya yung sarili niya para mag-value siya. Ipa-plus lang pala siya sarili niya para mag-value siya. So, ganito. So, ang value natin ng EBX natin ay 2. So, proceed to the next slide. Move EBX 123. So, EBX natin. Kung magbibilang tayo sa array, ang 0 at 1, ang magiging value ay 2. So, ang magiging value ng magiging siya, may table. Index 1. Kasi mabibilang ang 0. So, kaya 2 to. Equals to 123. So, ganyan lang mag-declare.
The continuation of Jamer's discussion, 86 addressing modes. For my first example, this is an example of direct offset addressing. This one uses arithmetics to modify address. This one move from the AL operand and adds the byte table plus 2. So the value of byte table will be added plus 2 to the AL operand. So to the next one, immediate operand. The value of 1 will be moved to operand AX. The direct memory addressing. It will move the value 102H to operand AX. Sa ARM addressing naman, register to register means i-move niya yung register 1 directly to register 0. Bali yung value ng register 1, ipapasa na kay register 0. Next one is immediate. Move yung 15 to register 0. In ARM addressing, there are different types of registers. First is R0 to R12, which are the general purpose registers. Next one is R13, is reserved for the programmer to use as the stack pointer. Next one, R14, is the link register which stores a subroutine, returns address. And the last one is contains the program counter and is accessible by the programmer.